of the system. Work flowing out of the system is indicated by a minus sign. And our cell potential and the work are going to have opposite signs. So our energy, our E cell, right? So our E cell is going to be minus W over Q, which is our charge. So the negative value for the work is going to be Q times E. So the maximum work in a cell would be obtained at the maximum cell potential. So our maximum amount of work is going to be our maximum cell potential times the charge, or our maximum work is going to be minus Q times E. Work is never the maximum possible if any current is flowing in any real spontaneous process. Some energy is always wasted. Right? Your electrons, you're not working with a superconductor probably. You're going to lose some energy into shot noise or thermal noise, or just the fact that reactions are reversible, right? And so you're not ever going to get anything going to 100% completion. The actual work realized is always less than the calculated maximum. But the actual work done is given by the following equation, where W is equal to Q times E, the actual potential difference at which the current is flowing, and Q, the quantity of charge in the coulombs transferred. So our Faraday, we said was the charge on 1 mole of electrons. Its value is 96,485 coulombs per mole. So Q is going to be the number of moles of electrons times the charge per mole of electrons. So Q is going to be N times F, number of moles times Faraday's constant. Our change in free energy equals the maximum amount of useful work. So remember this from the last chapter, W max, our work max, is equal to delta G. So now we can say our work max is equal to our charge times our potential, right, from electrochem, and delta G, which is equal to delta G. So we can rearrange this, and if we know Q is equal to NF, and we can say that delta G is equal to Q times E max, or we can say that Q is equal to minus NFE, right? So delta G is equal to minus NFE is tying together our thermodynamic properties with an easy to measure cell potential. So if you're doing electrochemistry, you have a very easy window into getting delta G, which we saw is going to be related to all those other things, right? Delta G, our energy, is going to talk about kinetics and thermodynamics. And now we're tying it into electrochem. So electrochemical cells are just lab scale thermodynamic experiments, and they're easy to do. And you can see why people were super excited back in the turn of the 20th century, going, oh my gosh, this stuff is awesome. All I got to do is get a voltmeter and some beakers, and I can make these thermodynamic measurements just by hooking some leads up to it. So for our standard conditions, delta G naught is going to be minus NFE naught. The maximum cell potential is directly related to the free energy difference between the reactants and the products in the cell, which means that we've got an experimental means to obtain delta G for a reaction. I don't have to sit there with a thermometer and do something where I'm going to measure the entropy of the system and do multiple experiments at different temperatures and figure out, well, okay, I can do that and I can backplot it up and get the slope as delta H and my intercept is going to be my delta S. Right? I can just hook up a voltmeter. And this confirms that the galvanic cell will run in the direction that gives us a positive value for E cell, because if it's minus Q times W, it gives you a negative delta G value. So a positive E cell means delta G is negative. And do you think we're going to be able to relate this to K? Oh yeah, we're going to be able to do that. All right, so let's look at an example. So using the data table in 17-1, we can calculate delta G for the following reaction. And we can say, is this reaction spontaneous? Well, what we're going to do is we're going to take our two reactions. We're going to make one a cathode. We're going to flip the other and make it an anode. We're going to add up our voltages together for a reduction and an oxidation to give us our overall cell potential. And we've got 0.78 volts, so delta G has to be negative. We're just going to do, what is our value for delta G? Well, it's going to be N times F times E. F is Faraday's constant. N is just the number of electrons. We're there. right? N is going to be 2 moles of electrons, because if we look over here, how many electrons were involved? 2. So N is going to be 2. F is Faraday's constant. We got our E cell, so delta G is going to be 2 times 96,485 coulombs per mole of electrons. My mole of electrons cancel out. Our E cell is going to be in volts, which is joules per coulomb. My coulombs cancel out. I'm left with joules. Boom, I've got a delta G naught value. If the spontaneous is spontaneous, as indicated both by the negative sign of delta G and the positive sign of E cell. This reaction is used industrially to deposit copper metal from solutions resulting from dissolving copper ores. Right, so if I want to get some copper, one of the easiest ways to do it is I'm just going to dissolve it in some nitric acid. Now I've got copper 2 plus or copper 3 plus, and then I'm just going to deposit it by taking advantage of the fact that I can react it with cheap iron. All right, so the copper will deposit out onto the iron. Your turn. Consider a cell that employs the following overall reaction. I got 2 aluminums and 3 iodines, giving us Al3 plus and 6 I minuses. What is the delta G for the cell? So we've got our 2 reduction processes over here, keeping in mind one of them is going to need to become an oxidation for you to do this. Okay, pause, come back. All right, you ready? You solved it? That's going to be minus 1,270 kilojoules per mole. So it's going to be a pretty spontaneous reaction. Obviously, this one became the positive one. You're going to get like 2.2 volts or something, right? And that's going to be plus 2.2 volts. E cell is positive. Delta G has to be negative. It's a spontaneous reaction. Using our data table from 7.1, we're going to predict whether 1 molar nitric acid will dissolve gold metal to form Au3 plus. Right? So sometimes if you've got gold, right, gold is called a noble metal. If I throw hydrochloric acid at gold, it's going to go meh, no big deal. If I throw sulfuric acid at gold, it's going to go meh, no big deal, not dissolve. What if I'm throwing nitric acid at it? Why is nitric acid going to work and H2SO4 and HCl won't? Well, what we're going to see is that we've got different kinds of acids out there. H2SO4 is what we're called a dehydrating acid. It's going to pull water out of things. HCl is just a regular old standard acid. But nitric acid, right, is going to be an acid that's going to gain a little bit of a boost because it's what we call a reducing acid. So our nitric acid is going to do some electrochemistry in addition to just moving protons around. Okay? So if I take my nitric acid, right, my half reaction for the nitric acid acting as an oxidizing agent. So here we're specifying, right, we want to, and we're saying, well, gold is going to go from gold solid to gold 3 plus. So we know that this gold has to be the oxidation, right? Because we're going from Au solid into Au3 plus, right? We are saying that the gold has to be the oxidation process. Ordinarily, if we were free to let nature take its course, we pick whichever one's going to be the most positive. Here we're saying Au has to be the oxidation, which means that the HNO3 is going to have to be the oxidizing agent, which means it's got to be the reduction. So a reaction oxidation for gold solid to gold ions, right? This is writing it out as the oxidation. It's because that's the way the problem is set up. This one is our reduction, right? Since these half reactions are going to give us the overall reaction, we're going to do either this is the version where you're subtracting the 2 table values minus E red from the cathode, and we're going to get minus 0.54 volts. Since it's a negative, the process will not occur under standard conditions. Now, if you take that and you mix it with some nitric acid and hydrochloric acid together, and you get something called aqua regia, sometimes given this little digraph, AR, is required to dissolve gold. So you're going to need to kind of mix 2 acids together.